Hello, everyone. My name is
Hello.
Philip, and I'll be here as tech support during this tutorial. I want to introduce you to our tutor, Marina Marjanovic. She is professor at Zingadunum University, and she will hold the building and optimization of neural networks from scratch with Numpy tutorial. Enjoy.
Thank you. Hi, everyone. Okay, since I'm presented already, nice to meet you this way. And from tomorrow, I will be on the conference. So today I'm going to present you building neural networks from scratch with Python implementation. And we are going to, I will present you everything, but analyzing case study movie recommendations. So I think that this example is useful because we can understand how network is built from scratch, implementing backward and backward propagation, and to understand how everything works in this network and how network is trained. So it's much easier to understand when we work from scratch than using TensorFlow library. So as you know, in the past few years, deep learning has generated many excitement in machine learning and industry, thanks to many breakthroughs result in, for example, in speech recognition, computer vision, and text processing. So for many researchers, deep learning presents another name for a set of algorithms that use a neural network as an architecture. So even though neural networks have a long history, they became more successful in recent years due to availability of inexpensive parallel hardware like GPUs. Also a lot of data that are available in the recently. And in this tutorial, I will start with the concept of a linear classifier and use that to develop the concept of neural networks. So I will present two key algorithms in learning with neural networks. So the stochastic gradient descent algorithm and also back propagation algorithm. So toward the end of this technical tutorial, I will explain some simple tricks and recent advances that improve neural networks and their training. So for that, I will start with one example immediately. So I will focus on case study for movie recommendations. So in this table, I presented the ratings for movies. So let's write a computer program to answer this. So it's Friday night, for example, and you are trying to decide whether you should watch the movie Gravity or not. So you ask your close friends, Mary and John, who already watched these movies, but they have different opinions about this. So both of them gave the movie rating of 3 in the scale between 1 and 5, and not outstanding, but perhaps worth watching. So given these ratings, it's difficult for you to decide should you watch the movie or not. So you have kept the table of their previous ratings for some different movies like Lord of Rings, Star Wars. And maybe you can use this data to decide if you should watch the movie or not. So the data look like they are shown in this table. So in this figure, I presented this rating graphically. So with O, we presented the movie that corresponds to I like the movie, and with X, I represented the movie I dislike the movie. So the question is, with the rating 3.3, should I like the Gravity or not? So let's use the past data and write a computer program to ask this. So for every movie, we can construct an example of X, which has two dimensions. The first dimension is the first feature, is Mary's rating, and the second dimension is the second feature, is John rating. And every past movie is also associated with the label Y. That means if you like the movie or not. So this label Y is actually represented graphically. With X, it's I like the movie, and Y, I didn't like the movie. So our goal is to come up with decision H of X. This is a decision function to approximate Y. So our decision function can be simple as weighted linear combination of Mary's and John's rating. So where x1 is Mary's rating, x2 is John rating, and b is a bias. And this can be also written in a vector form, like theta transpose x plus b. The decision function H unfortunately has a problem. So its values can be arbitrarily large or arbitrarily small. So we wish its value to fall between 0 and 1. And this is because we are using activation sigmoid function that is actually limiting our decision between 0 and 1. So the graph looks like this. We have, as I mentioned in this table, we have some past data, and we will use this past data to learn the decision function. So we have activation function where we are using Mary's rating and also John's rating for all the movies. So superindex Y1, 2, and them means that the order of the movie, actually. So the order of a sample, if we are talking about data sets. So X features, X1 and X2 will be our features, and superindex until M, we will imagine that we have M movies. So to find the values of theta, that it is parameter in our decision function, and also bias, we can try to minimize the objective function, which is actually the sum of differences between the decision function H and the label Y. So here is obtained the minimum squared error rate, the cost function like minimum mean squared error rate, when we are summing everything over all past movies that Mary's and John watched, and I already labeled them as I like or dislike. So to minimize this function, we can iterate through an example and slowly update parameters theta and the bias in the direction of minimizing each of the small objective, this h of theta minus y squared. So concretely, we can update parameters in the following manner. So we update the parameter theta1 equal to theta1 minus learning rate, the difference in theta1 that we made, and theta2 as well, and b. So alpha is a small non-negative scalar representing a learning rate in the gradient descent algorithm. And this, a large alpha will give aggressive updates, where on the other hand, the small alpha will give a very small updates, and the algorithm can run very slow. So such an algorithm is known as a stochastic gradient descent, and alpha is learning rate. So now the question of finding the optimal parameters amounts to find delta theta and delta b, the change in theta and bias. and they should be in descent direction. So our objective function is composed of functions, so we can use the chain rules to compute their derivatives. And the chain rule is very useful when we are talking the derivative of a function of functions. So thanks to of these chain rules, we know that the good descent direction for any objective function, it's gradient. So therefore, one example, xi, for example, this is a vector of Mary's and John rating for ith movie. We can compute the partial derivative for delta theta 1 and delta theta 2. If we had more people that rated the movies, we would update more thetas and the bias. So the steps in these algorithms are initialize the parameters theta and bias at random. Pick a random example of Mary's and John rating for ith movie and see your decision if you like the movie or not. Then compute the partial derivatives theta 1 and theta 2 and b, and also update parameters using those equations. So this is equation 7, and this is equation 3, 4, and 5, how you should update those parameters. So we can stop stochastic gradient descent when the parameters do not change or the number of iterations exceed certain upper bound. And at convergence, we will obtain a function of decision function h theta, which can be used to predict whether you like the movie or not. So if this decision is because we were using sigmoid function, and we can set up the threshold to be 0.5. So if this decision function is bigger than 0.5, we should like the movie, or 0 we shouldn't like the movie, and this is a decision boundary. So we can plot this decision boundary to have this, and the green line is the final decision function or the decision boundary, and any point lying above the decision boundary means I should watch, or below I shouldn't watch the movie. So as you can see, this gravity movie, it's something that you should see. By the way, we can represent a graphical illustration of this decision function, where we have only 3 neurons in our simple neural network, where we have neurons Mary's and John's rating input. We have parameters theta 1 and theta 2, and we have decision function where we are also adding bias at the end, and we are obtaining decision function. So this network means that to compute the value of this decision function, we need to multiply Mary's rating with theta 1, John's rating with theta 2, and add 2 values and bias, and then apply sigmoid function. So this is the most simple neural network that you can imagine. Unfortunately, there are a lot of limitations of these linear decision functions. And in this case, we were lucky because the examples here were linearly separable. So we can draw a linear decision function to separate positive from negative instances. So imagine that now your friend Susan has different movie tastes. So if you plot her data, the graph looks like this. So as far as you can see, those data, we cannot imagine one linear decision function to present the boundary of this. So Susan likes some of the movies that Mary and John rated poorly. And the decision is how we can come up with the decision function for Susan. So from looking the data, the decision function must be more complex than the decision function you saw before. And your experience tell you that one way to solve a complex problem is to decompose into smaller problems that you can solve. So we know if we throw away the weird example from the bottom left corner, the problem is simple. So similarly, we throw up weird example on this right corner, and again we have simple situation. So as you can see, this problem is composed on two linear problems. So this one represents the top right corner, and this one represents the top left corner. And now we have combination of two linear functions. So now we will, let's suppose, as we already stated, the two decisions, H1, for theta 1 and theta 2, and we have a bias B1. And we also have theta 1 and theta 2 bias 1, and we have already composed another linear combination of theta 3 for 3 and bias 2. And here, after this, we are obtaining omega 1 and omega 2 that they are representing the decision function after each linear combination. So we lay out the data in this table, and it would look like the first data, as you can see. So here we have, again, movie names. We have output by decision function H1. We have output by decision function H2. And we have the final decision for Susan ratings, yes or no. So now, once again, the problem becomes finding a new parameter set to weight these two decision functions to approximate the final decision y. So let's call these parameters omega c, and we want to find them such to find h of omega 1, omega 2, and see that it is new biased to approximate label y. So this can be done again with stochastic gradient descent. So in summary, we can find the decision function for a student with following steps. So we should partition the data into two sets. Each set can be simply classified by a linear decision, and then use previous section to find decision function for each data set. So then we can use newly found decision functions and compute the decision values for each example. So then treat these values as an input to another decision function, and again we can use stochastic gradient descent to find the final decision function. So of course this architecture can be much more complicated. So here maybe we want to hear another opinion, and again we can sorry, we can split our problem into smaller simple problems and have, for example, two layers. Here we had one hidden layer, here we had two hidden layers. So the input layer was Mary's and John's rating. So and Susan final decision. Here we had and we had two hidden one hidden layer. Here we had two hidden layers. So this is a famous special architecture in machine learning, knowing it's a neural network. So this is instance of neural network has one hidden layers, which has two hidden neurons. And the first neuron computes values for function h1, and the second neuron computes the value for h theta, the sigmoid function that maps real value to bounded value between 0 and 1 is also known as the nonlinearity of the activation function. So since we are using sigmoid function, we are limited to have values between 0 and 1. And this, in the future, you can encounter other kinds of activation function. I'm using a sigmoid data function because here we have a binary decision, yes and no. But this can be another topic, which activation function you should choose. So the parameters inside the network, like theta, omega, are called weights, and B and C are called biases. So if you have a more complex function that you want to approximate, you may want to have deeper network that looks like this on the right. So this network has two hidden layers. And the first hidden layer has two hidden neurons, and the second hidden layer has three neurons. And we can go back to our problem. So finding a good decision function for Susan. So it seems so far so good, but the above steps we actually cheated a little bit when you divided the data set into two sets, because you looked at the data and decided that these two sets should be partitioned that way. So is there any way that such a step can be automated? So it turns out the answer is also yes. So, and the way to do it is by not doing two steps sequentially, but you should do this in one equation and compute the final decision function like this. So you will find all these parameters, omega 1, omega 2, C, theta 1, theta 2, theta 3, theta 4, and B1 and B2 at the same time. So we can notice that the stochastic gradient descent is quite general. So as long as you have a set of parameters, you can find the partial derivative at each coordinate and simply update one coordinate at a time. So the tricks are to find the partial derivatives, and for that you need a famous algorithm knowing as a back propagation algorithm. So what you are doing actually in forward propagation with your input ratings, your input values, you are computing the final decision. This final decision will be something between 0 and 1 because we were using a sigmoid function. This value between 0 and 1 is our predicted value. And y is our known label, 0 if you didn't like the movie and 1 if you like the movie. So at the end, you will compute the error after the decision function. So in backward propagation, you will also go through the layers and compute the error, and the error will be our input value from the right side. So what are the steps in forward and backward propagation? We should perform a forward pass to compute decision function for the first movie, decision function for the second movie, decision, and so on. And for the output layer, we will compute the last output layer. Let's say that this is L. We will compute the error function and compute its gradient. So this is given with this formula, where this is a scalar multiplication. And with this gradient of an error, we will update parameters and perform a backward pass for all previous layer until we reach the first layer again. So for each node I in the layer L, you can compute the error in each layer for each neuron, and so this is given with this formula. And the desired partial derivatives can be computed like this. So this indices makes algorithm to look little bit busy, but we can simplify this equation using this element-wise dot product, that it is if B and C are vectors of n dimensions, then this product B product C is a vector A of n dimensions. And nice property of the back propagation algorithm, it is that it can be made efficient, because in the feed-forward pass, some of intermediate values can be catched, and then those intermediate values can be used to compute the gradient in the backward pass. So now I'm going to represent you, and I can also do it in Colab in front of you, but briefly I will give you a bigger picture what I'm going to do and how we can implement forward and backward propagation from scratch in Python, only using Numpy library. So here we can define the sigmoid function. We can define sigmoid derivative, because in backward propagation we are using derivative functions. And in the first, when we start with parameters, initially to update the parameters and training the neural, in the first epoch, in the beginning, we need to initialize our parameters. So we can initialize them at random, because this is the best way to initialize every single omega and every single theta. Because if you set up it to be 0, then the network will be 0 and you will not have updates. So the best way is to set them to be random. So you will have weights input hidden, like random, and the dimension of these weights input hidden will be the input size, will be in this case it is 2 Maris and John rating, and we will set up to have some hidden size. This you can choose which hidden size you are going to use, and also bias hidden. Also, you are going to create a weight hidden output, and dimension of this matrix will be hidden size times output size. And the bias output would be the number of zeros, 1, and output size. Here, output size will be 1, because we have only 0 or 1 at the end. So we will start with input size 2, because we have Maris and John's rating. We have hidden size, we can put that it is 4, doesn't matter, and output size is 1. And learning rate is, we can put something between 0 and 1, because if we put it in between 0 and 1, we don't have it 0, 0, 1. For example, it is not so fast and not so slow in gradient descent algorithm, and we can do it over, I don't know, 1000 epochs. So 1 epoch means 1 forward and 1 backward propagation. So let's create this code, and we will apply it on this case for movie recommendation and predict some new value. So here I already define it. So I will start from scratch if somebody wants to follow what I'm doing. So let's import the necessary library. So the only necessary library is Numpy. I will, what I'm using is Google Colab. So since you are not using any library, but Numpy you can use in every environment without installing anything. So import Numpy SNP. Then we should define some sigmoid and sigmoid derivative. So def of sigmoid of x. We should return one divided, this keyword, 1 divided by 1 plus NP exponent of x, of minus x, sorry. So if we have, for example, create some value x, like x equal NP dot line space, or between 0 and 100, for example, or we can from minus 10 till, oh, I could put minus 10 until 10. I need number of samples. In space, so we can say sigmoid x. And we can plot. Plot it, we can import matplotlib. Dot inline. This is not. And now we have a sigmoid function. Okay, this is sigmoid. Now we can create derivative of sigmoid. So def sigmoid derivative. What is sigmoid derivative of x? If x is 1 divided by 1 plus, but no, 1 divided by 1 plus e minus x, derivative of this is equal to actually x times, it's actually 1 divided 1 plus e power minus x divided by 1 minus stupid. So 1 plus minus x I can store on 2, and here I will compute the derivative of this is minus 1 times 1 minus derivative of 1 times this. So what we are going to obtain is derivative of x equal return x times 1 minus x. Then what we need to do is to initialize the neural network, and we are going to define this function. So we need to define to have input parameters like input size, hidden size, and output size. And we will initialize them on random. So let's define initialize parameters. And we will have input size. We will have a hidden size. We will have output size. Then we will have NP random seed to fix them. Random dot seed 42. Then we will have, so this is for reproducibility. Then we will create matrix of weights input hiddens, weights input hidden. Then we will have equal np dot random, and which dimensions we will have input size dot rand, np dot random dot rand, and here we will say input random also. Input random, and here we will have weights input hidden equal np dot random dot rand input size hidden size. Input size hidden size, and we will also create a bias hidden. There should be the same size. On add hidden neuron, we will add one bias, so the bias should be the vector of one hidden size. So be bias dot hidden equal np dot zeros. It can be zeros 1 comma hidden size. We should pay attention only on the matrix size, and we should know a little bit linear algebra, of course, to understand this, how it works, and to create those matrices. So bias hidden is this, and we should create weights hidden output. So weights the hidden output equal np.random.rand of hidden size output size. Size and bias output should be dimension of output size. So we can copy output size, output size, and we should have bias output. Bias output will replace hidden by output. Output size, and this is this, and we should return them all. Return. We can wait input hidden. Hidden. Then we can bias hidden. Then we have awaits hidden output. And we have bias output. Bias output, so let's run it. So if we want to initialize the parameters, so we can just to check what we got. And we have input size, let's say that this is 2. Two hidden size can be 4. And output size is 1 because we have rating 0 or 1. Let's see. So we got what we have, weight input hidden bias. So here we have why we have 4, because we have 2 inputs, but we have, look at this, we have 4 here, theta 1, theta 2, theta 3, and theta 4. And here we have for another layer. So here you can exactly obtain with which follow in each layer, you can follow all the coefficients that you have. So here those parameters represent the parameters in the first layer, and here are parameters in the second layer. This is the first hidden layer bias, and this is bias output, and this is final decision. This is actually bias output. This is weights hidden output. This is bias hidden, and this is weights input hidden for both neurons. And you can, when you start with updating over epochs, you can exactly see how those parameters are updated. So here you have a theta 1, theta 2, theta 3, and theta 4. Then you have hidden biases, and you have output bias here, and you have omega 1 and omega 2 for each layer. So let's now, when we initialize parameters and when we defined all the necessary function, we should define forward propagation. What we are doing what we need to do in forward propagation, we need to, here we will have X. X will be Mary's and John rating. Here we have two features, and we can have, for example, I don't know, 10 movies different. So we will go with input parameter with input X that can be some array. So let's say, for example, that X is some array of Mary's and John's rating. So we can create something like this: X equal np.array of, let's have, for example, let's take this example. Here we have this table for each movie. So we can put 1, 5. Okay. 1, 5. So we can put that, for example, 2, 3, 4, 2, 3, 3. Actually, we will keep this 3, 3 for prediction. So we can put 4, 5, 1, 1, 5. So we can create our X for input. And what also we need for forward propagation. So we need our weights that are initialized and that we will go in forward propagation with them. So let's define the forward propagation. Def forward, let's call this forward propagation as an input parameters. We will, of course, have our input. We will have our weights input hidden that we obtained here. Weights input hidden, what we will have our bias hidden. Have bias hidden, we will also have weights hidden output and bias output. And bias output. And what we are doing now in forward propagation, we need to compute the dot product between X and weights output hidden first in this layer. So we need to compute X and weights output hidden. So knowing linear algebra, you will exactly obtain those equations. Omega 1 H1 X plus omega, we want to obtain this. Omega, actually, we need first this one. We will obtain X times theta plus B and compute sigmoid of this to obtain this for each layer. So what we are doing here in forward propagation, we will compute the hidden layer input. So hidden layer input, which will be a dot product np dot of x, so before a sigmoid function. So x, we will have a weights input hidden, plus bias, but bias hidden. Also, we will have now, after dot product, we will have hidden layer output, which will be sigmoid of that. We will have a sigmoid of hidden layer input. Hidden layer input, and here I will call this output. And this is hidden layer output. And now we will have output layer input, which will be a dot product between hidden layer output and weights hidden output plus bias output, and compute sigmoid of this. So let's have hidden layer output. And depends on how many outputs you have, you can construct layer by layer, of course. For more complex networks, you will use library, but this example is good for understanding how forward and backward propagation work. So hidden output layer input. Layer input equal to np dot hidden layer output hidden layer output, and we will have weights hidden output and plus bias output. Bias output. And after output layer input, we need to have our final output, which will be sigmoid of our output layer input. And this will be, in this case, when we only have one hidden layer, will be our predicted output, sigmoid of output layer input, and we will call it predicted output. Equal sigmoid output layer input. And what we need to return is to hidden layer output and predicted output. And predicted output. So let's try to see what we are getting. So if we try this, we put what is weights input hidden what we obtained. This will not recognize actually the input. I think I cannot do this way. Yeah, because weights input hidden, I need to take them from here. Weights input hidden are this, so I will call them like this. Array, okay. Here I will need a bias hidden. Equal np dot. What is bias hidden here? It's np array of this. What else do we have? We have weights hidden output. Equal np dot weights hidden output will be this thread. And bias. What else do we have? Bias output. Equal np dot array of 0. This is after first iteration to see what we are getting. So let's define this. Unmatched y. This is okay. And we should obtain here. And we should call this forward propagation. So here it is after our forward propagation. This is our hidden layer output. And this is our predicted output. So here output run on input import, sorry. Define sigmoid, then we will start this. Sigmoid derivative, initialize parameters. For example, let's try this. Let's try this. Then we will have forward propagation. And let's define this, and then we will return this. Name predicted output is not. Predicted output is not defined. Here. It is what we are obtaining after the first forward propagation. So we are obtaining this vector. So let's now define we need to define the cost function. So here we want to obtain hidden output. This is array. Okay. Now we want to define the calculate cost. So define calculate cost, and we will obtain y true and y predicted. because we want to compute an error. And y dot predicted and we will compute the number of movies. In this case, this will be len of y true. Y true, and we will compute the cost function like mean squared error, cost equal 1 divided by m. One divided by m, and the cost will be times np dot sum y true minus y predicted square, like np dot square y true minus y predicted. Sorry, I didn't see that I have some messages. Okay. Think again. Is my screen black?
On my end, it's normal.
Okay. Thanks. So we calculate cost, and we need to compute backward propagation. So now I think I have here backward propagation to be sure that I will explain it. What does it mean? So here in backward propagation, not to type everything, so to try this prediction as soon as possible. So here we will have this backward propagation, where in backward propagation, we have our input layer, we have our true label of our ratings of the history of the past movies that you watched, hidden layer output, predicted output, weights input hidden, bias hidden, weights hidden output, bias output, and learning rate, and you are computing error output. So after first propagation layer, you have your final decision. This is actually 1 and 0 that you already had labeled, and our predicted output will be something between 0 and 1. So what we are, for example, if we obtained this, this as an output, for example, here the final decision will be 1, because we will set up the threshold to be bigger than 1, but bigger than 0.5. But we will create an error. This is 1 minus 0.88. Here we will also obtain some error. So our error at the end of the last layer will be y true minus predicted output. Then our output delta that we are going now in backward propagation from the last layer to the first layer, it will be our error output times sigmoid derivative. This is actually a derivative of our error output. So this is our output delta. This is error output times sigmoid derivative of our predicted output. Then we will compute the dot product. This is weights hidden output transform, output delta dot, this is output delta, wise product with weights output hidden transpose. Then we will compute hidden delta. Then when we computed this hidden delta, we need to update weights and biases. This is actually those equations. in backward propagation, and update the parameters delta theta and delta b. And we will return weights input hidden, bias hidden, weights hidden output, and bias hidden bias output, because those are updated parameters after the backward propagation. So in forward and backward propagation, we need to update them non-stop, and we will do it over the epochs and compute this cost function. So let's create, for example, let's run this code. So we will define the input size we already did to be 2, hidden size to be 4, output size to be 1, a learning rate we should write a learning rate equal to be 0, for example, 0, 0, 1. And we can run this over the, for example, 10,000 epochs. 10,000 epochs, and we will compute the weights input hidden. Input hidden. Also, our output will be bias hidden because of this, in this order. Bias hidden, then weights hidden output. Weights hidden output, and we will have bias output. Equal. Now we need to initialize our parameters. Initialize parameters here. This is something what we already did here. Initialize parameters after input size is not defined. How it's not defined? Input size. Because I put it here immediately. So input size is 2. Hidden size is 4, and output size is 1. To 1. And now we can initialize our parameters and obtain parameters to call forward propagation and to go over the epochs. So we can run this epoch. So we can, I will actually copy and paste this. So I will show you what I'm doing. And okay, we will print predictions. So what I'm going to run over 10,000 epochs, it means 10,000 forward and backward. And we are going to compute in forward propagation, we will go with this first time we are going to initialize parameters at random. Every next time, those parameters, when they are updated, we will update them and go forward and go backward and update them non-stop over the 10,000 epochs. And we will go with these initial parameters and with our ratings. Then we are going to compute costs. So for this, we need to compute vector y true, which will be n pi array. Which will be, for example, first movie we didn't like. How many, what is our x? How many? 5, for example. So for each sample, we need to define if we like the movie or not. So let's say that, for example, np array dot 1, say 0, 1, 1, and 0, let's say. So if we want to, for example, scatter those data, plt.scatter, we can scatter x of all rows and first column. This is Mary's rating, and we can scatter John's rating. And to have this, it's a little bit, I don't like how and color will be y. So we can make a realistic data as we had here, that color is y true. So this is my data. So of course, if I want to have something more realistic, I can increase my data set, for example. So I can put here 1, 4, 3, 2, 4, 1, 4, 2, 1, 3 to have something different, and I will increase this also. Y true will be, I will copy this and change it. You can put here, for example, 1, and we can put 0, we can put here 0, we can put here 1. So let's scatter this data so we will have something like this. And we want to, for example, we have some y test. Y test will be equal np dot array of, for example, this will be actually x test. For example, uh, 3, 3. And here we can plot scatter x test. And we can put here x test of all rows, 0 column. Here we have x test of all rows, first column. Inputted color is green. how it's we need another bracket. Is not defined. Green, it should be under the here it is our test point. So we can put maybe 2, 3. For example, to make prediction for this. So here we ran over the epochs in forward propagation. We went with X, first time only with initialized parameters, but those parameters will be updated here. So I will again compute this to update this those parameters after the back propagation. So here we have back propagation algorithm, and then we will test the trained network. So we have predictions, forward propagation, and when we start with forward propagation, we will compute our delta. So here we what we are obtaining in forward propagation, we are obtaining hidden layer output, predicted output. In backward propagation, we are going with this hidden, we have our X again for updates of parameters, but we have what is really Y true, but this is computed in forward propagation, hidden layer output and predicted output. And we also started with weights input hidden bias first time with initial parameters, and after that we are going to compute them again because we are updating them in backward propagation, computing the gradient and using gradient descent and trying to minimize this error. And every time in forward propagation, we are going to use updated parameters, but every time we will obtain our predicted output and hidden layer output. So here we will compute our predictions after predictions. What we actually need is after the forward propagation to obtain what we want. So here is calculate cost is not defined. Oh, we didn't calculate cost here. Okay, I am going to here calculate cost is actually only I think I did, but I where is this? Y true, Y predicted. So this is squared error between Y true and Y predicted. As far as I know that I computed this cost function. No. Here. Okay, what is np dot square? Something I missed, but anyway, I will. M is length Y true, return Y cost. So here, backward propagation, learning rate, and we are going to compute this. So here we are going to compute weights input hidden and to train over 10,000 epochs. And here you are going to get our final predictions. So here we were running over the epochs, and those are our final predictions for the for should we watch the movie or not. So print final predictions dot mean so our final prediction should say that we should watch the movie because it is above 0.5. So in this case, I presented you the neural network only with 2 layers. And with 1 hidden layer actually, and 2 features. This can be increased to have much more if we want to include Susan rating and others rating. Then we instead of building 1, imagine that you are using linear prediction. Here, it is much better to compose this problem into smaller set of problems and build a neural network and compute those weights for this in forward and backward propagation and make final decision. Since you know this, you can modify the number of layers, number of neurons. You can play with the sigmoid function to see what you are getting. So it doesn't have to be binary decision, but with this example, you can understand how you actually build a neural network from scratch. So I want to ask you if you have some regarding this tutorial. Copy and chat so we can continue the code. Aha, okay, I will send it to you. So here I can, here it is. I will download it. It doesn't have an error. Okay, just a second, I will send it over the chat. Any question?
Just make sure to, in the chat, put to everyone, not just the hosts and panelists, so it goes off to
I
everyone.
will. I'm going to do this. So, answer. If I go to answer, how I can answer to everybody? Sorry for share screen, so I will. If I put chat here, honestly, I don't use.
So above the chat, if you just click on chat, there's a two dots, and it says, it should say everyone.
Here. I think I can send it to
Okay,
you.
okay. If not, I can repost it to everyone.
Oh, okay.
Yeah, you sent it to hosts and panelists, so I'll just repost it.
Okay,
just download it real quick.
But since you understand this, how it is done, from now on, you can use, of course, TensorFlow or PyTorch library, and you will never actually do this from scratch. But this helps you to understand how you can build a neural network. Okay, that's all from me. I think I sent you the code.
Yeah, I just reposted it to everyone.
Okay.
So are you done?
Yes, it's up to 3. So I was computing, I was organized myself to finish this, and I left minutes for a question. So if you
no problem. If someone has a question, please do type.
Okay.
Okay, seems there are no questions.
Okay,
well,
thank you for your attendance, and see you tomorrow in Salad Center.
Yes, thank you, Marina.
Thank you.
And thank everyone else for watching. Goodbye.
Bye.